Okay, so this is a re-recording of the exam 3, spring 2018, on the problem pertaining to the electrochemistry. And I'm going to focus on 1 to 4, number 1 to 4 problem, because this is the one that has no sound, so I'm re-recording it. And sorry about it caused some confusion for you guys. So let me get on it and solve this problem again. Okay, so this is about the redox reaction. Something gets reduced, something gets oxidized, and then they want you to figure out the constant goes in front of H2C2O4 and the waters in here. So essentially, this is a half reaction problem. So let me get on to the half reaction. So I'm going to pick on the one containing the mangan. So MnO4 minus becomes Mn2 plus. Okay, so what do you do? This is as in acidic solution. So remember, this is actually with practice in Chem 1. Acidic solution means you are allowed to use H plus and H2O. And the sequence that you do is you balance the oxygen using water, and then balance the hydrogen within the H plus, and then at the end you balance the charges using the electrons. So this is a kind of sequence. So the oxygen first, you have a 4 oxygen on the left hand side. So I need an H2O I can allow to use, but I need to use 4. So there are 4 oxygen on both sides, and that's good. And then because by doing so, I generate 8 hydrogens, so 8H plus on the left-hand side will balance the number of hydrogens out. And finally, if you look at the charges, plus 7 in the left-hand side, plus 2 in the other side, so you need to essentially subtract those pluses by adding 5 minuses, so adding 5 electrons, so the charge is being neutralized. Okay, and the second one that I'm going to write is this one, which is H2C2O4, and then we are seeing the CO2 here. Okay, so let's look at that. First is, okay, I need to balance something like a carbon, so 2 carbons, so I need to write 2 here, and then makes 4 carbons on the right hand side, 4 oxygens on the right hand side, and the 4 oxygen on the left hand side. That's good. And so as long as I can balance it out, 2H plus, that makes everyone happy, right? And then is a neutral on the left hand side. I make it neutral by adding 2 electrons. So then it will be balancing the reaction. So in the reaction on top has 5 electrons. This is a reduction reaction, and the reaction at the bottom is an oxidation reaction. And what I want is I want to multiply this one by the top by 2. That makes it 10 electron. The bottom by 5. That makes 10 electrons. And then if you add them together, these electrons are gone, right? And then you have to retain what is remaining in the bottom. So the first part is 2 times MnO4 minus, and H plus is 16, and then you also have 5 times H2C2O4. Okay, so this first problem takes a little bit longer because you have to solve the problem very systematically here. And then this one is 2 times Mn2 plus, and then 8 times H2O plus 2 times CO2. Oh, not 2 times CO2. You have to multiply by 10. So that is 10 times CO2, and then the 10 times H plus. Okay, so the answer is right there, but to this 10 H plus, this is a 6 H plus survives, so that kind of tied it up. And then we got the water, and so water-wise, they want to ask the question: the waters and CH2C2O4. Where are you here? So you need a 5, you need an 8. So 5 and 8. So the number E is a correct answer to solve this half reaction. So this is once again, this is a reduction reaction. This is an oxidation reaction. You solve this problem by using the half reactions. And this one shows the reaction, the number 2, which cell notation for the redox reaction is given the following. And as you can see here, chlorine and is actually reduced into the chlorine ion. So essentially Cl2 is reduced. So there's I guess 2 electrons and 2 Cl minus. So that's a reduction. And then an oxidation in the here is that's how the oxidation occurs. So oxidation Fe is oxidized into Fe3 plus. You need a 3 electrons. Okay, so that's how I understand. And then what do you write in this notation is, I mean, if you want to finish that up, okay, I want to multiply by 3. I want to multiply by 2. If you add it up, you will get the equation showing up at the top, which is a 3Cl2, and this is gone, and then you have a 2Fe and 6Cl minus 2Fe3 plus. But by doing this diligent work, you realize there is a 6 electrons interchanges in this reaction, and that will be useful for defining the electrochemical potential using Nernst equation. But that's not the point of this problem. They just wanted to know this notation. So this notation is actually, they put anode, which is an oxidation, and then put what is called a reduction, not reduction, they call it cathode. This is always a electrochemist saying this cathode, that's a reduction, and that's the sort of the format they wanted to see here. Okay, so which one get oxidized? So once again, this one get oxidized, right? So you want to write Fe to Fe3. So that's the one, and which one get reduced? So let's see this one. Chlorine is getting reduced in the chlorine minus. So this is the one, the chlorine is getting reduced to chlorine minus. So if I just write this one as an answer, then I will just write, okay, the oxidation Fe changes into Fe3 plus aqueous. Good. And then this line means the salt bridges. Okay, double line means salt bridges. And then you're going to do the reduction, which is a Cl2 gas is become Cl minus in aqueous. And then I'm going to highlight this section here. If you hear there's no solid electrode portion that can finish up this reaction, the electrochemical cell notation. So then what people needed is they need to put some kind of a solid electrode, and then common choice is platinum or some kind of a carbon is the graphite solid. Okay, so you are expected to see, because none of them here are solid, right? So therefore they are putting this one right there is a platinum electrode. Because none of them, this one and this one, is not solid. So therefore, this is a correct notation. And the number 3 is actually, I like this problem. This one is quite nicely given. Their essential reduction potential. If you look at here, okay, I saw the reduction potential. This is the reduction potential. And if you look at that, which is a winner? This one wins, right? So what that means is I'm going to, in your top of your mind, okay, this is the one in the bottom is losing it. So the reaction must happen this way. Oxidation should happen. So an E oxidation potential should be plus 1.18 volts. Okay, so this is something that you should know. And then they ask you that using the standard half cell potential listed below, calculate the standard cell potential for the following reaction. Okay, and this is the reaction is a balance. So then you start to looking at it, the reaction. Okay, so by writing this, I can write Fe 2 electrons. Not 2 electrons. Fe and the electron is on F minus, whereas the mangan is being oxidized. So mangan is oxidized, mangan 2 plus, and the 2 electrons, right? So then, and then what do you need to do is, okay, not Fe. What happened here? Okay, F2 fluorine gas. Okay, so then in this cases I think there is something, I don't know what happened here. This one should have written as a 2 electrons. So that's why I got confused here. Okay, 2 electrons. Okay, so this is the correct reaction that's supposed to be written this way. And then what do you need is you need to add them up, right? This one goes away, and then I will get Fe Mn goes not Fe. I just keep on writing Fe. Okay, F2 when Mn goes to 2F minus and Mn2 plus. And to me, that says N is 2. Okay, I don't know what is the deal here, but let me just fix that up. But that's not the point of this problem, to have a balanced equation and do the Nernst equation. They essentially ask the central question. E reduced potential is an intensive property. Okay, so it's actually, it doesn't matter that how many what's the multiplication that you do, the top equation and the bottom equation, as long as E cell standard is on just a reduction and an oxidation that you do. And then so what you hear is 2.87 plus oxidation means 1.18 volts. As simple as that. Okay, so this is a 1. That is going to be the answer. So that's the one. So once again, it is on intensive properties, and I think that there's some kind of a confusion here because the electrons are not balanced in this equation. So I have to rewrite this equation. Let me just check it out before. It's because this is a plus. Yeah, so that's the correct. Yeah, I checked the exam reference sheet. This 2 is missing here. Okay, so this is so I've correct that, and then this whole problem is not correct. Okay, but we can still get the correct answer here. Let's move on to the calculating the equilibrium constant for the following redox reactions at 25 degrees C. Actually, this is a better problem set, because what you see here is they are showing this magnesium becomes Mg2 plus, is 2 electrons and then Mg reduction. So this is actually being reduced. So this is reduced as it is. And if you look it up, the Mg 2 plus and its value is actually Mg is minus 2.37. And then what you see here is aluminum. And so I want to start with something as simple. So aluminum 3 plus is 3 electrons, and you'll get aluminum, and the reduction potential for the aluminum here. And if you look at the aluminum 3 plus, that says a minus 1.66. Whereas Mg2 plus is something below with the minus 2.7. So who's going to win the game? This is the one that is going to win the game. Right? So that's the way it should be, and the reaction should occur the reverse way, and this becomes essentially has to be changed into E oxidation, which is a plus 2.37. Okay, that's where the spontaneous reaction. But if you look at the equation up, it doesn't look that way, right? So the aluminum 3 plus is being actually get reduced. So we just have to follow the notation that is shown up here, and then we can essentially think about things happening in the reverse way. So at any rate, this one, let's just continue to the traditional one without first ignore this the way it is written. And we can do this one by multiply by 3, this one by multiply by 2. I'm just talking about the reaction in the reverse way, which is an oxidation. Reaction happen in the forward way, which is a reduction. So by doing so, and you will see the case where okay, so that's what I'm talking about, 3 mg, all right, and then the one that 2 Al3 plus. Moving on to the 2 times Al naught plus 3 times Mg2 plus. Okay, and so here's once again what I mean by E cell. This is an intensive property. You might have an impression that because I multiply this 3 times, 2 times, should I multiply this by 3? Should I multiply by this 2? The answer is no. You don't do that because this is an intensive property. So all you gotta do is just change these numbers into the oxidation potential, change these numbers to the reduction potential, and you will find that E cell potential here is 2.37 minus 1.66. And then there will be 0.71. So because the cell potential is positive, it is this reaction is spontaneous, right? But now the way that is written up there, this equation is now, it is a reverse way of this. So I'm just simply write this one this way, this is a problem. So this reaction, the cell potential will be on the opposite, which is a minus 0.71. So that's an information. I come a long way to get this data right away. But if you don't do all the elaborate procedure, you can quickly get these answers. Okay, this is a non-spontaneous reaction. actually the aluminum is oxidized. That's actually not favored because that should be reduced compared to the magnesium being oxidized, but in here the magnesium is reduced. So this is a electrochemical standard potential from the cell, and then I was able to get the negative answer, which is a non-spontaneous reaction. And also, but by doing so, you can get actually very important information, what is called the N. The N here, if you look at the way how many electrons are involved in this reaction, 6 electrons are involved. So N is 6 is the information that you got it to use. Okay, so therefore I am going to write it down, the equilibrium potential. Okay, so then I'm going to look up the, let's see, let me have a look at it. The one that you see here, this is from the reference sheet, that E cell is RT NF LNQ. Am I right? So that's the one that electrochemical potential is actually not LNQ when it's LNK, right? And that's what when this is true. So this is what I find out, and then they wanted to calculate the K. So let's plug in the numbers, which is minus 0.71 volt, and then RT is 0.31 8 I think that I'm getting tired. Okay, 8.314, and the temperature, I'm pretty sure it says somewhere, so 298 Kelvin, 25 degrees C, and you have a 6 electron involved in this reactions written in here, right? This is N is 6 here, so N is 6, and then 96500 is a Faraday constant multiplied by lnk, right? So you just got to solve this one for the lnk and then k, and then the answer that I got is something like 8.7 to the 10 to the minus, let me see, what do I see here is lnk was as far as I know, lnk is a minus 166, and then I was able to get the numbers, the k value with 8.7, 10 to the minus 23. And this one is kind of a 8.9, I think the 73, not 23. 73, and this one is essentially none of them has a correct answer, so that's, I think that's what happened, but this is the closest one, so I will choose this answer for my answers. So here I re-record the answer key for the exam problem for the spring. This is a spring 2018 problem 1 to 4. Okay, and then the rest of the one is you can find the one with an audio, so you guys can solve this problem answer key on the LMS. Okay, thank you for your patience.